Okay, class number 9 on a Friday. Already gave this lecture. All right, so here's class number 9. We're covering Bernoulli and the energy equations, and this is sort of like the second class where we're covering Bernoulli. There'll be a couple more. And here we're going to introduce types of pressure and head. So where'd you go, guy? There you go. So here you go. Wetted is demonstrating 3 types of pressure that are in the Bernoulli equation. The first one is sort of a constrained type of pressure. It's a pressure due to confined space, the pressure that acts in every direction. Sometimes we'll call this the static pressure. And the second one is the dynamic pressure. There he goes. See, he's flying through the air. This is the pressure because of velocity. And then we have the pressure, the hydrostatic pressure. That's because of the water column that's above you, right? So 3 kinds of pressure. And when we're going through something like a Venturi tube, which is what this thing is kind of representing, we can change the type of pressure. We change from a static pressure that's got some dynamic pressure, and we increase the dynamic pressure, but the consequence is that the static pressure drops. And it can drop so much that we might even change phase, and called cavitation. It could be a very bad thing, cavitating. But then as we constricted, but then we can expand again, converging, and then we diverging, a converging, diverging nozzle. We can recover that static pressure. It can go back up, and it could even go back up even further when we maybe come down and we slow things down. All right. So this image represents a pitot tube, P-I-T-O-T, pitot tube. And it works on the idea that we can, at the point right here at the tip of this pitot tube, we actually stop, right? So there's a stagnation point. Because of the stagnation point, we generate what we call a stagnation pressure, which is the combination of the static pressure and the dynamic pressure together. We've turned the dynamic pressure completely turned it into static pressure, and we can picture that. And then if we have 2 gauges, this one's just covering only the static pressure, we can see the difference between the static and stagnation pressure, and we can figure out what the dynamic pressure is, and from that we can come up and measure the flow. Well, actually, first we find the velocity, and then from the cross-sectional area, with that we can get the flow. So that's sort of like the big ideas. This actually kind of belongs, I think, in the next class. But we could see that we could use Bernoulli to estimate how much water we can siphon out for a given distance between the inlet and the outlet. So that's kind of a neat thing. It's one of the many uses of Bernoulli for things. So let's see. Let's go and take a look. What's going on here? How come this is not moving? Oh, you know what? I think I have the wrong slideshow. Let me change slideshows. And wouldn't you know it, I had the wrong one. So I had moved that the siphon one into the next class. So here you go. We'll start out with this physical interpretation of Bernoulli's principle, and I'm going to call this first equation, we'll call it Bernoulli 1. We got this from using F equals ma, and we applied it to a chunk of fluid along a streamline. And in order to get to the Bernoulli, we made 4 assumptions. Steady flow, right? So that doesn't mean that flow is not accelerating. This means if you take any point and along and you took a look at it, and regardless of the time, that would be the same conditions. So it's a steady flow. Inviscid, so viscosity is not involved. It's not stealing energy away from the system. So that's an important part of the limitations of Bernoulli. Incompressible flow, we can only use Bernoulli when we have incompressible fluids or nearly incompressible fluids. So there's a limitation when applying it to gases that the gases can't be start to get incompressible, and that usually happens around when Mach number is about 0.3, right? And then it also needs to be along a streamline. So we have the idea of streamlines to kind of picture what's taking place flow either inside something or around something. We can have these lines that represent paths that particles might take, and we only can apply this to things that are happening along a streamline. We say that we have pressure, and then we have, so this is the static pressure. Here's the dynamic pressure, what we refer to right here, which is really, you can see this is mass times acceleration thing that's going on. And then we also have like the weight, which is the hydrostatic pressure. So we have static pressure, dynamic pressure, hydrostatic pressure. And that's equal to a constant along a streamline. And what that means is that we could take this at state 1 or some particular location where we know some things about that flow, and then we can go down a streamline, and we know that they're going to be equal to the same parameters, but now at the new location on the streamline. Another way to think about Bernoulli is to think of it as in terms of energy. And so I think I'm going to actually, in a class coming up soon, we're going to use Reynolds transport theorem and energy to rederive Bernoulli. But right now, let's just think about it in simplest of terms and just take a look at what for Bernoulli 1, that form of the equation. What are the things representing inside it? So I say, what is the definition of work? And that would be force through a distance. Now I say through a distance, and technically these should be vectors, and there should be a dot right here to say that it isn't just force times a distance. It's got to be the force times a distance that's in line with the force, right? So they have to be, it doesn't matter if you have force time that's perpendicular to a distance. That's actually going to be like moment or torque, that kind of thing. And if it's not moving, it's not actually performing any work. That's hard to concept sometimes to come across. But so just to reiterate, let's see, I can write on top of this thing. I believe I can. So let's go red. I said I should have dot right here. And so if you have a force like right here, and it moves from right here to right here, dot, 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 it's only the distance, it's only the force, this force right there, right? So, and so it's this part of the force, let's say the force times the cosine of that angle times this distance moved right there. That's what's generating work. But anyway, so the units are going to be pounds foot or foot pounds. So let's just take a look as a simplistic way of investigating Bernoulli, what the units work out to be. Well, first off, we know that in US units we're using pounds per square foot for the static pressure. For the dynamic pressure, we have slugs per cubic foot, and we have foot squared per second squared because we've squared the velocity. But if you take a look and you see this part right there, like if I cancel out one of those and I make that into a square right there, this guy right here, this is a pound, right? A slug foot per second squared is a pound. So we have pounds per square foot, all right? We've shown that. And then we have for the hydrostatic pressure, we have pounds per cubic foot. Well, that just crosses one of those out, leaves that with 2. So we have pounds per square foot. So we see that this is dimensionally consistent. That's a really good thing to check in any equation you're using. And then we want to multiply. If we multiplied by volume, see what would happen here, right? We would have, these would cancel out right there. And of course, we just learned right there that we would cancel out a bunch of these things right here, that we would have like, boom, that would cancel out and that would cancel out. And we would see that we still had that pound right here. So we have a pound times a foot, right? So we have a foot pound here, or a pound foot here, and we have a pound foot here, and then the same thing right there. We would cancel those out, and you'd have a pound foot. So what we've discovered just from the dimensions is that Bernoulli is really an energy per volume type of equation, or it could be, right? We're not necessarily, did we prove it? We just showed with the dimensions, that's something that's possible, and it turns out it is true. So when we look at this equation, well, we're looking at pressure. We can also think of it as energy per volume. That's an important idea. All right, so on here, I'm going to tend to look at this interplay between these types of pressures, right? So we have kinetic pressure, or sometimes I call it dynamic pressure, potential energy, or hydrostatic pressure, and then we just have static pressure. Well, if we would take a look at this spot right here, we have a plunger and we're pushing a force, and we can imagine that we have like a streamline that is moving from here to there to up to there, right? I didn't do a good job of that straight line. It wasn't not straight at all. Let's go to purple, better learning color. If we started at 1, right here, if we're far enough away from, we're a little ways away from the plunger, and we're a little ways away from the exit right here. So what we could say about this kinetic is going to be very small, right? At this state 1, or at this location. The potential energy, well, we could decide that that's going to be the datum. So if that's the datum, and we can choose the datum where we want, but that's a good spot, the lowest spot in there, we could say it's 0, right there. And we can see with the pressure, well, the pressure is going to be the largest that's going on right here. And if you were to add up these things right here, that, and that, you'd end up with a constant. I think you can actually even read that underneath it. You can actually, I don't know if you see that closely. You can see that my letters have been, yeah, kind of, I don't know, at least on this screen, you can see it's written on there. At state 2, we have just exited the nozzle, right? So we might even want to zoom in onto that thing, right? And here's our liquid coming out. And we're going to have our fastest, our largest amount of speed out of this thing. Therefore, our kinetic is going to be a large force, or is large dynamic pressure. The potential is going to be a little bit larger because we're up a little bit higher right here. So we'll call it small, right? It isn't 0 as it was at 0.1, but it is small. The pressure, now this is going to be interesting, is why I have it over here. Like, so let's say that this is our point right there, 0.2. Well, take a look at the pressure that's like right next to it, at a spot right next to it. They'd have to be equal to each other, right? They're not, because remember, pressure acts in all directions. Therefore, even though we might think of this as having pressure, it's going to be equal to atmosphere, which we treat as 0, right? That's going to be our condition. So you have to put a little thought into it to make yourself believe, because we'll refer to stuff as that being pressure coming out, but that's really the dynamic pressure, not the static pressure. Static pressure is the same in all directions. And then, but if you add up these things together, they come out to be constant again. That's the idea of the constant along a streamline. I don't think I have to write out constant every time, but maybe I will. And now we move up higher here, and we're going to get to the very top where we stop. And this we often will call a free jet, that we shot straight up into the air, and it can only go so high. So it actually becomes 0 there. The potential energy now is going to be large. It's going to be at its largest. It is traded off with this scenario. And the pressure will now be 0 as well, right? Because it's going to be atmospheric pressure, right? It's not going to go in any direction. But this is also constant. So it's good to kind of think of along those lines, and there's some applications that we'll run across, like a free jet, maybe that's something. We can almost use this as a means of even measuring our, the amount of pressure in something. It can be used by just measuring how high it can shoot up. Now, another way that we can measure, or another way that we can apply Bernoulli, and I usually call this Bernoulli 2, right? No, actually, that's Bernoulli 1. Oh my God, did I jump over Bernoulli 2? I guess somehow I jumped over. I guess I didn't include him in the slides. So let me switch over to the camera, and I can talk about Bernoulli 2. All right, so I think I did this in class too. Same mistake. Okay, so here we go. Here's Bernoulli 2. So this is another version, very standard version, very common version that we will use to express Bernoulli. And it's the idea of what we call head. It's an old school thing where we divide through by the specific weight. And we refer to this collection as the pressure head. And here we'll notice that the density went away and we just have gravity on the bottom right there. That's because, before we had density right here, but we've divided by gamma, which remember is density times g, so the density goes away right there. And what we're left with is v squared over 2g. And then, of course, we divided out the specific weight, gamma, so now we're just left with z. And we have this idea, and this is, okay, so this is the velocity head, and this is going to be the elevation head, right? So we use these names head, and you can think of, in the Navy, we call a bathroom a head. And I almost kind of think of it like the toilet in The Godfather 1, right? And you remember he goes to the bathroom to get the gun that's hidden behind the toilet there, right? And he's got this is the old style type of toilet where they would pull a chain, right? They'd pull a little chain right there. Well, this is like a head tank, right? We even have something we call a head tank for some applications. So we're really using the idea that the elevation of something can be related to the pressure of the thing. I mentioned in class on ships, quite often, it could be a steamship or it could be a diesel reciprocating engine ship. So like in the system, like in the cooling water system on board a ship, there'll often be a tank that's high up in the engine room, and it'll have a level of water in it and a pipe coming all the way down into the system, right? Just attached to the system, right? So there's the piping system, and it might go. There might be a pump right in here that's moving water through a heat exchanger right there, and it's going into the engine. There might be a filter involved too. Let's put a filter in there. Maybe we want to put a filter in before the heat exchanger. Well, whatever. But it goes into the engine. There's the big engine, whatever. Draw it like that. I don't know. Looks like a big coffin. But anyway, it's a big engine, and it comes back out. Comes back out the other side, and so we have this circulating system right here, and maybe there's cooling water coming from the ocean right in there. But this tank serves to set what this pressure is going to be. That pressure has to be this elevation right here. This elevation is like a pressure regulating system into this thing, making sure that this pump, because it's hot water, right? So one amongst the things that you don't want to do, and the heat exchanger might be on the other side, by the way. But hot water will make this pump cavitate. So we're going to keep a pressure in this system all the time by having this head tank. And we might even have like a little float valve that might be in here that's going to be connected to like maybe a fill, right? Because there might be leaks or something along the line, or even just evaporation or whatever. So we will keep this tank at a certain level. But you could think of this as head, right? This H as being a thing that's going to control what the pressure is right there. So I just think it's a good idea to use these terms and get used to them, but also these concepts. And I think I have a long enough video now that I can go and stop it.